Hello everyone, my name is Pedro Araújo and today we're gonna talk about the research called a review of fuel injection for hypersonic air-breathing propulsion. This work was developed in collaboration between Instituto Tecnológico de Aeronáutica, Instituto de Estudos Avançados and Universidade Federal do Rio Grande do Norte. And the authors are David Romanelli Pinto, Luiz Soares, Israel Rego, Pedro Araújo and Paulo Toro. This work discussed and reviewed the full injection and flame holding techniques, the strut-based, the single and double cavity-based, and the backward-facing step full injection. Here is present the summary, so let's start the presentation. Currently, the only way to access space is through multi-stage space vehicles, usually non-reusable rocket engine, which carry the chemical combustion propulsion system on board, extract and convert chemical energy into kinetic energy with high efficiency, about 97–98%. Approximately 90% of the vehicle's weight at the time of launch is due to the propulsion system, a fuel and oxidizer, and the structure. So, still, according to Pratt, the oxidizer represents 60% of vehicle's weight at the launch. Too expensive system for space access. So, one alternative is the usage of hypersonic air-breathing propulsion, which could be less expensive than usual rocket engines. The University of Queensland in Australia developed the high-shot scramjet with undergraduate and graduate students, demonstrating the supersonic combustion in 2002. In 2004, the supersonic combustion was successfully demonstrated by NASA X-43S at Mach number 7 and 9.6, burning hydrogen for 10 seconds. Also, the US Air Force accomplished the X-51 flight at Mach number approximately 5 for 140 seconds, burning hydrocarbon. So, in general, a scramjet is an engine that operates at hypersonic velocities and can be divided into three main components: the inlet, combustion chamber, and expansion section. The breakdown cycle is used in thermodynamic analysis, and the terminology used is the reference station presented by Pratt. So, in the mixed configuration, the inlet is divided into the external and internal compression sections. The conditions required at the inlet design are the shock on lip, where all incidental oblique shock waves converge to the collide edge, and shock on corner, in which the reflect shock wave meets the combustion chamber entrance. The deflection angles are determined by inlet optimization and the conditions required at the combustion chamber entrance, usually temperature or pressure. Pratt indicated that for scramjet vehicles flying at velocity corresponding to Mach number 10, the residence time is about 2 milliseconds, considering a scramjet with 30.5 meters length, which does not exist in scramjet so far. So, a scramjet with 2.7 meters long, designed at the Universidade Federal do Rio Grande do Norte, has a residence time of about 0.7 milliseconds, flying at velocity corresponding to Mach number 6.8. As we can see, the supersonic combustion, the residence time is in order of milliseconds. Therefore, a full air mixing and stabilization of supersonic combustion flames are some of the main issues that must be addressed to hypersonic air-breathing propulsion. These works discussed and reviewed the full injection techniques and flame holding techniques, the strut-based, single and double cavity-based, and backward-facing step full injection. The strut-based has a series of technical issues in practice, and the single and double cavity are highly appropriate full injection techniques. The Hi-Fire 2 used two opposite cavity-based flame holds, burning a mixture of ethylene and methane. So the backward facing step is a variation of a single or double cavity based. Bezerra, in 2020, numerically investigated the influence of scramjet flight velocity in supersonic combustion. In three cases, Mach numbers 6.4, 6.8, and 7.2 were analyzed, and the hydrogen was transversely injected at sonic speed and with a temperature of 300 Kelvin into the supersonic airflow. The results for a single and double injection are presented, and the temperature control indicates hydrogen burning near the wall surface. The water mass fraction control steps up what was mentioned before. The hydrogen burning near wall surface is indicated by a high percentage of water in that region. Carneiro, in 2020, present the conceptual design of scramjet demonstrator using two approaches. The first, disregarding viscous effects, and the second, considering them by evaluating the displacement thickness using Chapman-Robertson model. Theories of oblique plane shockwave and Prandtl expansion coupled with the area ratio were applied in the analytical analysis. The supersonic combustion was modeled by heat addition in one-dimensional flow, known as Rayleigh flow theory, which is a simplified combustion model. Considering viscous effect, the static temperature increases while decreases the airflow velocity at the combustion chamber entrance. Keeping the flow supersonic at the combustion exit, the heat that can be added to the airflow is reduced, as we can see in the total temperature rise compared to both cases. The total temperature of the airflow increased due to the heat addition, so how much more energy is added, higher is the variation of total temperature. At the hydrogen injection location, a uniform and constant heat addition across the height of the combustion chamber was assumed as 950 kilowatts, equal to the heat added in the analytical approach. The pressure increased from 107.7 to 148.2 kilopascal, and however, when the same heat is added at one station close to the wall surface, a shock train was established, similar to transverse hydrogen injection simulation in Bezerra in 2020. So we can see the shock train begin at the region where the heat is added, increasing the temperature and pressure. When a wedge was installed downstream at the opposite side surface of the heat addition position, incident oblique shock wave was established and converged right away on the heat added. That intends to simulate the transverse hydrogen injection. The oblique shock wave impinge on the transverse flow injection provide a simultaneous combination of the expansion wave from the wedge and the reflex shock wave originated from the incident shock and the both shock due to the heat added near the wall, trying to model the transverse hydrogen injection. As shown, this intensifying the mix of the hydrogen air, increases the temperature higher than the hydrogen ignition temperature, and may provide an insight into hydrogen air combustion flame holding capability due to the better hydrogen air mixing and combustion. This study was finished in part by CAPS and was carried out with the support of Academic Cooperation Program National Defense. The authors would like to thank the Instituto Tecnológico de Aeronáutica to support granted to research hypersonic Airbreathing propulsion. Also, the third author would like to thank the Instituto de Estudos Avançados, and besides, the last two authors extend their gratitude to the Universidade Federal do Rio Grande do Norte. Finally, the first author would like to thank the Simulador Tecnologia de Trânsito and Group TecnoWise for the enthusiasm dedicated for hypersonic. And that's all, guys. I really appreciate your attention, and I hope to see you later. So, bye bye, guys.